Okay. So I would like to start this talk by looking at the several traditional examples of when do people run an experiment. In this first example, this is probably one of the earliest works in this literature of experimental design. It is some earlier works dating back to this Cochrane 1941. In this work, it is one of the first applications of experimental design when they apply to the agricultural applications. And in this setup, they run an experiment on different feeding plants, whether they feed the roughage or they feed the grain to their cows. And they run this experiment over the winter time, and they have 18 cows at that time, and they're trying to understand what is the different feeding plants on the effect of the milk yield. In the second example, it is some more recent examples of the clinical trials. And in a clinical trial setup, in this example, this HPTN network, they run this experiment in Africa in, I think, in 7 African countries. They recruit the participants and give them a different new dosage of therapy. So they were trying to compare if this new therapy is going to be effective in preventing the HIV disease, then compared with an older version of the FDA-approved therapy. In the third example, it is an industrial experiment. In this industrial experiment, this group of people, they published this paper back in 1999, where they were trying to compare different manufacturing specifications, these parameters, on the effects of the number of defects when they are manufacturing these printed circuit boards. And then the fourth application goes back to this social and educational experiments, where in this famous experiment conducted at the Tennessee, state of Tennessee, they run this Project STAR program, which is to understand if reducing the classroom size during the K-12 education period is going to be effectively increasing the quality of education as measured by their tested scores. So basically, they involve about 6,000 students, and then they were assigning them to different classrooms of different sizes, and then at the end of the day, they're comparing the test scores of the students from different classroom sizes. And in the last example, this is an application that is being adopted nowadays by many of these tech companies. For example, at Uber, they ran an example in February 2018 to test if the Uber pool, say when you're using the Uber pool app, then should you be immediately matched to an ongoing route, or should you wait for maybe a couple more minutes before they match you to a rider? And they run this experiment across 12 major cities in the United States. And they would like to evaluate the effectiveness of the waiting time when they're doing the matching. And they're trying to see how much would the cancellation rate increase if the customers have to wait for longer before they see their drivers. So with all these applications, we say that there is a pair of notions that we refer to as treatment and control that we're trying to evaluate how good is one better or worse than the other. And this better or worse thing is what we usually refer to as a treatment effect. So in all of these applications, we refer to usually the sample size as the total number of experimental units involved. In the agricultural experiments, these are the 18 cows. Or in the Uber example, it will be the 12 major United States cities. So that's what we refer to by saying a sample size. And when we're running experiments, practitioners usually recognize that running an experiment with an excessively large sample size is going to be costly in many ways, logistically and operationally. So it is a core question in the experimental design literature of how do we use the samples in an efficient manner. which is the purpose of this tutorial, where I'm going to adopt a optimization framework to examine such data efficiency questions. So by no means is this tutorial exhaustive in looking at the literature. There are several important omissions. So in this talk, I'm only going to focus on a narrower scope of experimental design for causal inference. But there is a broad literature on experimental design in general, which I will not touch upon. And one leading example in that would be the optimal experimental design literature, where people draw materials from statistics, optimization, linear algebra to study what is the optimal experimental design, but not necessarily for the purpose of causal inference. With that, I'm also omitting the important literature of optimal Bayesian design literature. And thirdly, in the area, if we focus on the narrower scope from experimental design to experimental design for causal inference, then in the narrower scope of causal inference, there are two popular frameworks that people look at. One framework is called the potential outcomes framework, which I will talk about in details in a few minutes. And the other framework is called the structural causal model approach. Some people also say it's the causal graph approach. And I will not be touching upon this second approach. But these two approaches are very popular. They're complementary to each other. If you're interested, you can refer to that literature too. So I'm going to adopt a potential outcomes framework to look at the experimental design problems for causal inference. And to start, let's look at only for one single experimental unit. I'm going to just define a bunch of concepts and then try to generalize to multiple units. On this very single one unit, then people usually refer to there is a binary treatment. And this treatment can take value either 1 or take the value 0. And then people usually say that when W is equal to 1, this stands for treatment. And when W is equal to 0, this stands for control. And in the Uber example, here the treatment would be to ask the passengers to wait for a couple more minutes, whereas the control is to immediately match the riders to the drivers. And we're going to adopt, throughout this tutorial, I'm going to use a capital letter W to stand for a random variable, where a small letter w stands for one realization of this random variable. So I'm going to formally adopt this potential outcomes framework, where I postulate this one pair of two different potential outcomes. Think of there are two parallel worlds. There is one treatment world, which gives you the y of 1, and there's one control world, which gives you this y of 0. Of course, you are not able to observe both of them at the same time, but you can only observe one of them. So at any point in time, in the Uber example, you can observe what is the cancellation rate of the riders. So the observed outcome is connected with the potential outcomes using the following expression, which is to say that if I do treatment today, I'm going to observe y of 1. That's my observed outcome. So y is equal to y1. And if I do control today, then y is equal to y0, meaning that I observe the control outcome. Yes?
I'm new to the causal inference, but I'm wondering, in this kind of binary treatment, you don't have to make like 0 and 1 to be something opposite statement. For example, in hypothesis testing, we need to make h0 and h1 totally opposite to each other. It seems like here we don't have to do anything like that.
Right, yes. So in the hypothesis testing literature, like the null hypothesis and the alternative hypothesis have to be like complementing to each other. That's exhausting the test space. But here, they do not have to be on the opposite. Just think of there are two policies that you're interested in testing. And sometimes they are aligned in some way. For example, you can be contrasting letting the riders to wait for 2 minutes versus letting the riders wait for 5 minutes. So they're pretty much going in the same direction, but just abstractly we say there are two versions of treatment. Yeah, if that clarifies your question. Okay, thanks. Oh, by the way, any question, just interrupt me at any time. Feel free to raise your hand. Okay, and I am going to be looking at the causal effect as defined as follows, which defines the contrast between treatment and control, meaning y1 subtracting y0. So this is the quantity that we would like to estimate. In the Uber example, this example could be just how much does weighting increase the cancellation rate? Like how much percentage increase in the cancellation rates do you see after you do the treatment? And as I mentioned earlier, so out of these two potential outcomes, you can either observe the treated outcome if you do treatment, or the control outcome if you do the control. So there's no way you can directly observe both of these outcomes at one time. And in order to estimate the causal effect of interest, you can only observe one of the two quantities inside the expectation directly. And you have to come up with a way to come up with a counterfactual value. What if there was the opposite treatment? And this missing data challenge is referred to as the fundamental challenge of causal inference from this Holland 1988 paper. So this is essentially the core question that we're trying to address. How do you address this question? Usually people generalize to multiple units. And when people make proper assumptions of how these multiple units are related, people can come up with an estimate of the counterfactual value. So let's try to generalize from one single unit to multiple units. So let there be n experimental units, and let the treatment assignment be taking this vector form. So previously, it is just one single treatment. But right now, if there are multiple units, we have multiple treatments. So it's captured by W, W1 to Wn. And once again, I'm using capital letter W to stand for a random variable, and I'm going to use small letter w to stand for a realization. It's because these treatment assignments, they can take values from a huge space of 2 to the n. So there should be, in the most general sense, 2 to the n that many potential outcomes. So there are so many 2 to the n many parallel worlds. So there are 2 to the n such potential outcomes for any single unit. Before I move on to talk about the assumptions, let me take a pause to see if anything is OK so far. Because this potential outcomes idea is really the core of this tutorial. I want to make sure everything is OK so far. OK, if there's no question, I'll move on. So usually, people would like to make assumptions, again, to try to come up with the estimate of the counterfactual value. So we would like to make the following 3 foundational assumptions here. The first assumption is to say that there is no interference between the units. In other words, what is being treated, like if there's another unit that is being treated or controlled, that unit's treatment assignment does not affect my outcome. In the Uber example, it could be just as simple as whatever is happening in Boston does not have an impact in San Francisco. So that the treatment assignment in Boston is only local. It does not spill over to the San Francisco area. So this is what the first assumption of non-interference refers to. Many of the time, this non-interference assumption holds if you're running experiments at the regional level. Whereas in some cases, you could possibly be thinking of maybe if I am a passenger and I am moving from Boston to San Francisco, so that the treatment assignment that I receive in Boston would change my prior and then change my user behavior. So that is going to be reflected onto the San Francisco's treatment. If that's the case, this violates the non-interference assumption. And if that's the case, we refer to a rising literature as the interference literature. And there are many active research happening over there. Under the non-interference assumption, we can basically focus on only the treatment assignments that we receive. For example, the observed outcome of y of j is going to depend only on the treatment assignment of wj, but not the treatment assignment of anyone else. So that's a shorthand notation that I will be keeping from now on. This is the first assumption. The second assumption, we're going to, oh yeah, go ahead. No worries. In this example, it's at the city level. Yes. So, because I'm looking at the 12 cities as treatment and control, and WJ could stand for whether Boston receives treatment or control. Cool. Yeah, thank you. Any other questions? Yes, within the same city, everyone receives the same treatment or control. Yes. The outcome is going to be the average cancellation rate in Boston. Awesome. So, oh yeah. Very good question. It is beyond the scope of this tutorial, but it's definitely generalizable, of course. Cool. All right. The second assumption that people are usually going to make to connect all the multiple units is to say that these units are generated in a homogeneous way. In other words, these units are IID, so that what I observe from one unit can tell me something about the other units. So that's the idea of the second assumption of the homogeneity assumption. Under this assumption, we have the following intuition to say that no matter which city it is, Boston, Denver, LA, whatever, these cities are homogeneous, so that a treatment in Boston could say something about the counterfactual in San Francisco. If in San Francisco we do control, then we miss the treatment outcome in San Francisco, and we're going to use the treatment outcome in Boston to create the counterfactual for the treatment in San Francisco. So that's the idea of this homogeneity assumption. Of course, in many practical applications, this homogeneity assumption may not hold true. For example, the East Coast and the West Coast, they have totally different populations, and the temperature and weather are totally different, so that what is happening in Boston may not be reflecting what's going to happen in San Francisco at the counterfactual. If that's the case, this violates the second assumption, and we're going to refer to that as treatment heterogeneity. If that's the case, this leads to another active literature in trying to estimate the treatment effect heterogeneity, or heterogeneous treatment effects. And that is beyond the scope of this tutorial too, but if you read the tutorial, there is an overview, there's a review of the most relevant papers in this area too. So after we make these assumptions on the data generating process, we are usually able to define the following two effects of causal interest. So the first effect, we refer to that as the average effect of the population. So we would like to use our experiment being conducted at the 12 United States cities to generalize to the entire country. In other words, we would like to use the data to reflect what is going to happen if we generalize it to a broader population. In other words, in some sense, we're doing the science discovery. And so in this case, we define tau as the average effect of the population, where we take the expectation over F, where F stands for the data generating process. And we usually refer to this as the sampling-based perspective, because the only source of randomness would, not necessarily the only source of randomness, because the causal effect of interest that we look at has a source of randomness coming from this sampling perspective. We're sampling the data from the superpopulation. So we take the expectation over F. The other perspective, people usually refer to this as the design-based perspective, where under the design-based perspective, while we look at the data, we only explain the data. We do not make the attempt to generalize to the broader population. Many of the time, if we're a business unit, we would like to explain what is the effect of a promotion, what is the effect of a matching algorithm. Sometimes we may only care about this single experiment's data, but we do not attempt to make the scientific discovery and generalize to the overall population. If this is the case, we refer to this effect as the average effect of a finite sample. And we refer to this perspective of estimating a causal effect defined in this way as the design-based perspective. We use the design base because we're running an experiment, we're designing an experiment, and this experimental design is the only source of randomness to this problem. And so here, we're using the small letter y, and we treat these y values as conditional values, or these y values as fixed values. Whereas in contrast, the sampling-based perspective, we're thinking of the y's as random variables, and we're taking the expectations over the y's. 1 minute. These two perspectives are highly related because if you take the expectation over the second term, over the design-based perspective, this average effect of a finite sample, then in expectation, you're going to obtain the average effect of the population. Question?
Yeah, so I'm wondering why is summation over 1 to n instead of, like, let's say, n1 number of cities receiving treatment 1 and like n0 number of cities receiving treatment 0. Why is not the average of these two and the minus each other the sum of all? Because I imagine the cities that did not receive the nuclear policy change, they wouldn't even have yj0 value here.
Yeah. Yeah. I guess you're asked, like, I guess the quantity that you talk about is the estimator that we use because we can directly observe those y's. So we're using the estimator to estimate this quantity. Yeah, so that is not the effect we're interested in estimating because it depends on the treatment assignments. But here, we would like to estimate one quantity that is not dependent on who receives treatment and who receives control. And your proposal is a good estimator to estimate this quantity. Yeah. 2 questions, maybe the back first.
You mentioned that n refers to the number of cities you consider
Yes.
in this case.
Yes.
I'm wondering whether the number of data you have for each city
Ah.
should have weight on this
Very good.
equation.
Yes.
New York versus then, let's say, New York should have weight.
Yes. Yes, definitely. So when we're estimating this quantity, we can definitely put different weights to the different units, to the different subscript j. That's of course doable. Just for simplification, I'm defining it in this way.
Yeah. So when you do this average effect of the population, which cities go for the treatment versus the control? Is there a random assignment or anything is fine?
Very good. So when we're defining the quantity that we would like to estimate, it is irrespective of how you do the treatment assignments because there is a ground truth that we would like to estimate. And when we talk about how do we estimate it, then it comes to our decision of who to do treatment and who to do control. Yeah, and later on, I will talk about a framework for you to decide how to choose those who receive treatment, how to choose those who receive control. Yes. Thanks for clarifying. Yeah. For one city, you can only directly observe either yj1 or yj0. So you're always missing the other one. So for one single city, you cannot directly estimate this quantity. Uh. Mm-hmm. I think so. If I understand correctly, I think the answer is yes. If there's a way you can generate multiple copies of data from one single city, for example, through measuring it at different periods. And if you, of course, there's another dimension of homogeneity that you will need to assume, of course. Yeah, if that answers your question. Cool. All right. Cool. So basically, we are going to, so far we talk about the quantity we would like to estimate. We're talking about what is the ground truth that we're trying to estimate. So moving on, next we will talk about how do we estimate these ground truths. So when we're doing this estimation, we usually resort to the following assumption of random treatment assumption. So usually when people are constructing estimators, people would rely on this assumption to ensure that their estimators are working. What this assumption says is that whether this unit receives treatment or not, or who receives treatment, how many receives treatment, I mean, like this treatment assignment, W, is independent of the potential outcomes of all the units. So basically, I cannot cheat by looking at the potential outcome of this unit, and depending on how big or small it is, I do the treatment assignment. I can't do that. And one very easy way to satisfy this random treatment assignment assumption is to conduct a randomized experiment. So how do we conduct a randomized experiment? Rigorously, an experiment is defined as a discrete probability distribution, eta. So here, eta basically refers to the probability that my entire assignment vector takes the value that we're specifying here. So this entire discrete probability distribution, like these probabilities, they should sum up to 1. This will respect that this is a probability distribution. And whenever we're talking about we're designing an experiment, we're choosing this distribution of experiments. I have 2 examples to illustrate what do I mean by saying one distribution. The first example, I'm showing a Bernoulli design. So in a Bernoulli design, we're flipping an independent coin for each unit to determine the treatment assignment of that single unit. And we can calculate what is the joint probability distribution, eta W, in the following expression. So basically, when we're flipping the independent coins, we can count what is the probability of the first unit receiving treatment, the second receiving control, the third unit receives treatment, and so on and so forth. So this joint probability can be calculated as the probability that the first unit receives treatment, which is p to the power of this indicator, times the probability that the second unit receives control, which is like the 1 minus p to the indicator. And we can multiply together. This gives us the joint probability distribution of this assignment vector. In the second example, we refer to a completely randomized design as the following, as defined by the following joint probability distribution. Intuitively, we're doing card shuffling here. Out of a total of n units, we are randomly shuffling them so that we pick the top p times n many fraction cards to receive treatment. And so then the joint probability is going to be equal to 1 over n choose pn. And then if the total number of treatment units sum up not to p times n, then this treatment assignment vector just have probability 0 of being selected. So that is the completely randomized design. So, question? Okay, cool. Oh, yeah.
So, right in the assumption you say the assignment and the treatment are independent.
Mm-hmm.
So is it okay that I say I have, let's say, 10 outcomes so far, and I use this 10 outcomes so far to determine the next one, which one it should receive the treatment or not? Because it is still independent based on this 11 individual, but it is not independent
Very good. So I think Eugene is asking this question of, is it possible that depending on the first 10 units outcome, I'm going to adapt on the outcomes, and then I choose the treatment assignment of the 11th unit? And that would violate this assumption, because here this assumption is very specifically saying that the treatment assignment of one unit is independent on the Ys of all the units. Not only this unit itself, but also all the other units. And this question actually leads to the third very active literature, which is called adaptive experiments, where this assumption would break. But conditional on the past observations, you can say that my treatment assignment is independent from my potential outcome. And this conditional independence thing would help you construct a martingale sequence, and you can apply some of the results over there, although some other results may fail. But that's a very active literature that people are currently working at. In other words, these three foundational assumptions, each failure, each violation leads to a very active literature that people look at today. Thanks for asking. So now I have talked about this treatment assignment vector and what is the probability. And we're referring to this joint discrete probability as an experiment. So the next step, we would like to look at what is an experiment and how do we design an experiment. So when we design an experiment, sometimes we would like to make the following assumption. Sometimes this is not so critical, whereas sometimes some other people would like to make this assumption, which is to say that the marginal treatment probability of every single unit is strictly between 0 and 1. In other words, the treatment assignment should not be deterministically 0 or 1, like treatment or control. But the treatment assignment, sometimes people restrict that to be random, to be strictly between 0 and 1. And when p is not equal to 0 and 1, then the Bernoulli design that we talk about of coin flipping and the completely randomized design that we talk about by looking at the card shuffling, both of them satisfy this positivity assumption. So after we run an experiment, we would like to estimate the causal effect that we talked about earlier. So people use estimators to estimate the previous quantities that we look at. So these estimators can be designed in a wide variety of ways. And I'm only introducing the two most popular estimators. The first one is called the difference in means estimator, which goes back to the earlier question of we take the samples from the treated cities and we take the samples of the control cities. We take their respective averages and then take the difference. And then this will lead to the following difference in means estimator. We simply take the difference between the two sample means. The second estimator is referred to IPW estimator, which IPW stands for inverse propensity weighting. And this IPW estimator is basically, instead of putting a random quantity of how many units do we do treatment, this IPW is going to replace the random quantity by the probability of receiving treatment. And then intuitively, what this IPW estimator says is that we're weighting each sample Y by the inverse propensity 1 over the probability of this unit receives treatment. And so this defines the IPW estimator. And both of these estimators are very popular in the literature, and there are lots of works on studying these types of estimators. And one quick exercise that we can do is to say that no matter, so far we talk about 2 randomized designs and 2 estimators. No matter which combination we choose, we always can unbiasedly estimate the treatment effect, the causal effect that we're interested in estimating. So if we further take the expectation over the data generating process, then the average treatment effect from the sample is equal to the average treatment effect of the population. So any combination of the 2 estimators and the 2 designs will lead you to unbiased estimator of the 2 causal effects of interest. And then one immediate question is, all 4 of these combinations are unbiased. Which one shall we choose? Which one works the best? And that is the core idea of this tutorial, that we're going to examine which one is the best. And we're going to propose a framework to examine which one is the best. OK, so this is essentially a decision-making question, because we're choosing what is the best thing to do. This is a decision-making question. And this statistical decision-making literature has been pioneered by Abraham Wald in the 1940s. And to the best of my knowledge, this Jeff Wu 1981 paper is one of the first one that studies using this decision theoretic framework to examine the experimental design problems. And this framework is very, very powerful, but in the literature, this paper is under-recognized and under-cited. But this is truly a foundational paper in this area. So to apply the statistical decision-making framework, we usually define a loss function first. So this loss function is a function of our treatment assignments and of all our potential outcomes. It depends on all of them. And one common choice of the loss function is to take the square loss if we're interested in estimating this effect of the causal effect. So we take the difference between our estimator tau hat and the quantity that we would like to estimate, which is the tau. And then we take the square loss. And this is the, one of the most popular choices if we're doing estimation. Although, if you're doing hypothesis testing, then this loss function can be binary, either 0 or 1, or you can define it as the penalty of making false negative or false positive claims, which you can definitely choose a different loss function. So from now on, I'm only going to focus on this estimation problem and focus on this loss function as defined as a square loss from below. And if we evaluate the loss function across all the scenarios generated by the experimental design, then we can take the average loss by taking the expectation over the randomness coming from the design. And we refer to this as the risk function. And overall, people would like to minimize the risk of an experimental design. So we write down this risk minimization problem. And this risk minimization problem, it depends on several things. It depends on the eta, which is our design of experiment, our decision. It also depends on y1 and y0, which are the unknown environments, because we do not know the potential outcomes. So we are essentially solving a decision-making problem under uncertainty. We're choosing the eta when the potential outcomes are unknown to us. If the y1 and y0 are known to us, then this problem becomes very simple. Basically, if they were known to us, we don't even have to run this experiment. We can directly return what is the effect of treatment. But if we still want to run this experiment, then this is a deterministic optimization problem, where our choice of the experiment is eta, and we would like to minimize this function that is well-defined if y1 and y0 were given to us. But the more interesting questions will come from when the y values are unknown to us. If for some reason we have a prior knowledge of the y values, then this is the stochastic optimization framework, because we can minimize the risk function where the potential outcomes are sampled from a known distribution. We're minimizing the expectation of this risk function. So this is a stochastic optimization problem. Alternatively, we could also adopt a robust optimization framework to look at this question, where instead of examining the y's by assuming a prior on the y values, we are now minimizing the maximum risk of this risk function, where we postulate an uncertainty set And then we can choose the y1 and y0, the potential outcomes, to come from this uncertainty set. And this is at the well-known robust optimization formulation. And if you're more advanced, you want to collect some historical data and build an uncertainty set around this historical data, you can as well do the distributionally robust optimization problem too. So a key comment I want to mention here is that whichever formulation that we choose reflects our modeling of the uncertainty. If we collect historical data, if we trust it, we use it as a prior, then this can help us do the stochastic optimization. Or if we don't have a historical data, or if we don't believe in it, we want to be robust, then we will usually choose the minimax framework. And sometimes, because we're talking optimization, the minimax framework sometimes is easier to compute than the stochastic optimization problems. So again, it really depends on our modeling choice of the uncertainty of the unknown potential outcomes. I guess I can take a pause here to see if any questions, because this pretty much concludes the first module that I wanted to talk about today. Yes, go ahead.
Yeah, so I heard this concept about when design experiment, we should kind of, for example, let's say heart disease and some medicines, we should make the treatment and control group, their age to be kind of similar to each other. This kind of matching of the kind of background, and how this concept can fit into the framework you talked about.
Yes. So Adrian is asking, what if the experimental units are different? They have different baseline heart failure rates. They have different demographics information. And so to answer this question, I will point to the assumption 2 of the homogeneity assumption. So basically, this violates the homogeneity assumption, which I will talk too much about the details here. However, we can model the y's as a function that depends on the baseline covariates. So instead of simply writing y1 and y0, we can just write the y's as a function of the x, of the baseline covariates, depending on some dependent variables. And we say this y of x under treatment and y of x under control. And again, that is the very hit literature on treatment effect heterogeneity that people look at nowadays. Cool. Thanks. Other questions? Cool. All right. So for the remaining of this tutorial, I will be showing some examples of how do you apply this framework. And I will be particularly diving into the minimax robust optimization framework just as an illustration of what's happening. If you're curious about the stochastic optimization framework, you can refer to my tutorial paper where I have a section on stochastic optimization over there too. Okay, so now let's look at the, oh yeah, sorry. I see. I guess it depends on, for example, whether they can build a prior using historical data or not, or from similar experiments that they can transfer into this new setup.
Well, part of the reason I asked the question is because if they can't build a prior and they use a framework where they can't, they might underestimate the amount of uncertainty that's actually present.
I see.
By ignoring the fact, so the fact that I can't build a prior actually means there's a huge amount of uncertainty.
Right.
But I might miss that point if I take a perspective that sort of eliminates that uncertainty. So that's kind of where the question is.
Gotcha. Yeah, then maybe somewhere between stochastic and minimax, maybe like you could model the y's to be dependent on the uncertainty, like on something that you know, and then building off from that, there is another layer of uncertainty that you don't know, and that would potentially lead to some interesting works. For example, Defun sitting over there, we're exploring something with Jeff together right now of leveraging some information that we know for sure are going to have an impact, whereas there's another layer of uncertainty that we don't know. Yeah, so there are different ways basically to model the whys, give it a different model, and yeah, so yeah, try our best to build the models for the whys. Yeah, if that answers your question. Yeah, thanks. Cool. Okay, again, let me see if there are any questions that I missed before I talk about the examples. Okay, cool. So for the next 30 minutes, I'm going to talk about the robust optimization framework. And one leading example would be the Jeff Wu's paper, this 1981 paper. And in this paper, they give a model to these y values. So maybe partially answer the previous question. We can incorporate models to the y values here. So in this model, the alpha W stands for the effect of treatment, where alpha 1 and alpha 0 stands for the effect of treatment and control. And G of J here is referred to as the unit fixed effect, where different units have different magnitudes of effects. And also here, the epsilon J of W is the idiosyncratic noises that people assume to be unknown to us, but we know they are of zero mean, and they have equal variances. And this equal variance assumption is referred to as the homoscedasticity assumption. And I guess back in the 1950s-ish, the experimental design literature diverged into two big directions. And a group of statisticians, they go after this homoscedasticity assumption, and they build a very rich literature called the optimal experimental design literature, where under this homoscedasticity assumption, you can estimate a bunch of the coefficients, and they have to scalarize the estimation error of these different coefficients. So that is a very deep and rich literature over there. Whereas the causal inference people or the econometrics people, they go another route, and they look at, for example, heteroscedastic assumptions, where they don't assume the variances to be equal, and they build a very rich literature on generalized least squares and other methods. That is another direction too. So going back to this model, we have assumed this unit fixed effect model, and we're going to collect this unit fixed effects in the following vector form. And we're going to refer to this calligraphy G as the domain that the different units can take the values from. So this paper makes the following assumption of permutation invariance. So to define this permutation invariance assumption, we would like to first define what is a permutation. So simply, a permutation permutes an element from 1 to n to another element from 1 to n. And we will require this permutation pi to be invertible, meaning that it is a 1-to-1 mapping. And then we're going to define the permutation group capital Pi as the group of permutations that contains all the n factorial many permutations. So basically, as long as it is a 1-to-1 mapping, it belongs to the following permutation group. Here's an illustration of what is a permutation. So each arrow refers to what is going to be permuted from one element to the other. For example, here, we're permuting element 2 to element 1, permuting element 1 to element 3, permuting element 3 to 4, 4 to 5, and 5 back to 2. So this is an illustration of a permutation. And then because the permutation is invertible, it is a 1-to-1 mapping. So we say this pi inverse of 1 is basically reverting the arrows. So this pi inverse of 1 is 2, this pi inverse of 2 is 5, and so on and so forth. So we're going to reload the notation of a permutation now if the argument of the pi function is not a scalar, it's not an element, but if it's a vector. Then we say that the permuted vector G is going to be a vector of values that are basically permuted from the previous place. So here is an example of a permutation on a vector. So if this vector is such that unit 1 takes value 2, unit 2 takes value 4, unit 3 takes value 6, so on and so forth, then under this specific permutation, this permutation is going to give us a second vector. And the second vector on the first element is 4. Where does the 4 come? The 4 comes from the second place, the second value of the previous vector. And this permutation permutes the first value to the second place. And so this is an illustration of a permutation. So now we define the permutation invariance assumption. This assumption is to say that if the G vector is an element of the domain that we can take values from, then any permutation, when you apply it to this G vector, the new vector is going to be an element of this domain G as well. So with that being said, if we permute this vector, then the second vector is also belonging to this G set. If we further permute the second vector, we have the pi of G. Then this new vector, the third vector, is also an element of the G set. And if you can further permute to the fourth vector, to the fifth vector, and finally, if we permute the last vector, it will go back to the original vector. So it means that the permutation invariance basically assumes that all of these vectors belong to the G set. Intuitively, this is to say that the domain of the values is symmetric. So if on the first element, this element can take values 2, then all the other elements, they should all be able to take the value of 2. This is the symmetric assumption that people assume here by assuming the permutation invariance. And the original paper is more general. I'm only looking at the permutation group that contains all the permutations. But if you want to partition the group into several smaller groups, and then within the smaller groups, you can do the full permutation, that's also fine. The original paper is fully general in that sense. But for this tutorial, I'm only introducing the simplest permutation group. So now let's try to apply all that we have talked about to the framework that we have illustrated about 10 minutes ago. So the causal effect that we're trying to estimate, which is the tau, as defined as alpha 1 minus alpha 0. This is the effect we would like to estimate. Alpha 1 is the effect under treatment. Alpha 0 is the effect under control. We would like to take the difference. We would like to use the difference in means estimator here. So usually when we're designing an experiment, what we'll have to do is to commit to a well-defined estimator. And we only choose the design. Whereas there are other literatures, they fix a design, and then they look at different estimators. For example, the difference in means estimator, IPW estimator, or some of the semi-parametric efficient estimators like augmented IPW. So that is a second literature. And people usually do that from an observational study perspective. But usually from an experimental design perspective, when we want to formulate it as an optimization problem, the degrees of freedom is too much if we allow both the estimators to be flexible and the designs to be flexible. So usually people just fix the estimator and choose a design, optimize over the design. So now we would like to commit to the following difference in means estimator. And we would like to choose the following loss function, which is the square loss. And then we would like to define the following minimizing the maximum risk here. So we define it using the following expression, where the maximum layer comes from the uncertainty of the G set. But we have already assumed that the G set is permutation invariant. So we restrict the adversarial nature when we're playing the zero-sum game to solve this minimax problem. So one quick comment to add on here is that if we design an experiment from a minimax perspective, usually, as we have all known from game theory, that when we're playing a zero-sum game, usually the optimal policy is going to be a mixed policy or a randomized policy. Think of when we're playing this, this rock, scissors, paper game, then the optimal strategy is going to I randomly play rock, scissors, or paper using probability 1/3. So this is a traditional thinking from the experimental design literature that the experiments should be randomized, and it can be justified through this minimax framework because the consequence of adopting a minimax framework is that the experiment should be randomized, which partially answers the earlier question. And alternatively, if you can model the uncertainty very well, and if you adopt a stochastic optimization framework, then many of the time the optimal design is going to be deterministic because the uncertainty is pretty much known to you, and you are not afraid of the worst case risk in some sense. And in the statistics literature, people sometimes refer to the external validity when people sometimes talk about this minimax risk, because people want to make sure the experiment is randomized to hedge against the external shocks to gain the external validity. So on the next 2 pages, I will quickly introduce the Wu 1981 paper's results. In my opinion, this is a foundational paper, especially this framework is foundational. And so I'm going to quickly talk about what does this paper say. So for any design of experiment eta, recall that this is a discrete probability distribution. So we can define the following new distribution as eta tilde. And through some very nice, very cute combinatorial arguments, this paper says that starting from any design of experiment, I can create another design of experiment that weakly achieves a smaller worst case risk. And how is this new experiment created? It is by taking the average over all the permutations that we can possibly have, and then just average out what is the probability of this vector of trivial assignment from being adopted. And then after showing this lemma, basically this paper says that the optimal experiment should take the form of a completely randomized design. And then the remaining question is, if we're doing a completely randomized design, how many do we do treatment? How many do we do control? And we can do some mechanical probability calculation to figure out the optimal experiment should be having half treatment and half control. And this very nice structural lemma is shown by using the Jensen's inequality by taking the by leveraging the convexity when we swap the summation and the maximum. And if we do this, if we sum the summation mark and the maximum mark, then we have the convexity there to apply the Jensen's inequality. And this one is sort of the middle ground experiment because we're taking the average across all of those probabilities. And this is the minimum risk one. So that's about the very foundational 1981 paper. I will spend the next 5 minutes to quickly show you the second example of the robust optimization framework, where so far we have seen a earlier model of decomposing the potential outcomes as the treatment effect part, as the unit fixed effect part, and as the idiosyncratic noises part. But right now, potentially we can assume a different model. So here now, let's only focus on the design that is Bernoulli design, parameterized by this vector of treatment probabilities. So basically, each unit can receive a different probability of treatment. And then we adopt a different way of modeling uncertainty, where we directly model the y values to take the values between a bounded set, where we assume this bounded set to be from negative b to positive b. And we don't need this b to be known to us. This can be unknown to us. And then a uniform uncertainty, under this assumption of a uniform uncertainty set, we can look at the following causal effect. The following causal effect is the average causal effect from this finite sample. And then we choose our favorite estimator here. Here we just choose the IPW estimator because that goes very well with the Bernoulli designs. And we define the loss function again to be the square loss, and we look at the minimax framework. We formulate the following minimax optimization problem, where the y1 and y0s are the unknown potential outcomes, and the domain of this y1 and y0 would be highlighted over there. It's too long to put it down here. It's highlighted in the red term, so that for every single unit, the domain is between negative b and positive b. That is the uncertainty set of the outcomes. So then this problem can be simply solved by doing some very simple, basic probability calculations. And I will just quickly show you the lemma, which is that many of the time when we are trying to solve the minimax problem, we will start from the inner loop maximization problem to characterize what is the adversarial nature's dominating strategy. Because in game theory, we usually look at what is the dominating strategy. So we can come up with the following minimax formulation. We can look at what is the dominating strategy of the adversarial nature, and then solve this problem. And the optimal solution is going to be that the optimal Bernoulli design is going to do 1/2 probability treatment and 1/2 control for every single unit. And that solves this problem. This is a very simple illustration to show that when we're running an experiment, why sometimes we want to do half treatment and half control. So this one is the building block of the third example that I'm going to give on switchback experiments. So now let me talk a little bit about switchback experiments. Going back to the example from Uber, we can run multiple types of experiments. Like some of the questions came here earlier, that we can run the experiments at the user level. And if we run this experiment at the user level, then in this example, let's say we're incentivizing the drivers to drive more frequently, then some of the drivers receive treatment and some of the other drivers receive control. So in this example, if we run the experiment at the user level, then we're assuming there is no interference between the drivers. But that may not be true, because if I got incentivized, if I drive for 2 more hours today, I am possibly going to take away the rights from the other drivers on the road, so that even though the other driver maybe doesn't change his or her driving style, that driver who didn't receive my treatment that got incentivized is effectively being decreased in terms of the number of completed drives. So the interference assumption might not hold true if you run the user-level experiments here. At Uber, they also can consider some other types of experiments being conducted at the city level, which is the example that I mentioned earlier. Uber conducted this experiment at the 12 cities in the United States in February 2018. And they run it in a synthetic experiment fashion, where in this setup, they do not assume Boston and San Francisco are the same. They recognize that cities on the East Coast and the West Coast, they're just intrinsically different. So when we're running the experiment, even though we can group all the drivers within the same city all together and only do treatment and control at the city level, so this basically solves the interference issue. But a city like Boston is different from a city in San Francisco. So we're not making an apple-to-apple comparison. So this violates assumption 2. And in order to get around with that, we will have to come up with, for example, the baseline covariates. We can use the historical data to calibrate it too. And at the end of the day, the bottom line is that we should make apple-to-apple comparison. We should correct it to make apple-to-apple comparison. And this leads to the synthetic control experiments, which is a way to design the experiments by making apple-to-apple comparisons. The third piece of experiment that people usually run is the switchback experiment. Under the switchback experiment, we usually think of all the units as a whole unit. But instead of running it at the city level, we run it within the same city and split it, treatment control, split it across the time. So we're running a time split experiment. And for example, we can do treatment in day 1, control in day 2, and then treatment day 3, control in day 4. So we're always switching back and forth between treatment and control. And that's where the name switchback experiment comes from. So I happen to have some works in the synthetic control design and also the switchback design too. So now let's quickly look at how do we define a switchback experiment. In a switchback experiment, we usually only have one single experimental unit, but we have multiple time periods. The single experimental unit in this case could be the Boston metropolitan area. And then there are multiple time periods. And in the Uber example, they can run this experiment for 2 weeks. And they can, for example, choose a search price to last for the next 160 minutes, roughly 2 to 3 hours. And so here, one experimental window is about 160 minutes. And so there are a total of capital T, which is equal to 126 periods overall. So the treatment assignment time T is W of T. And then in Uber, 0 stands for the flat rate pricing, for example, and 1 stands for the surge pricing, for example. And then we're going to collect all the treatment assignments into the following assignment path. And then we're going to say this random treatment assignment is capital letter W, and the small letter w stands for 1 realization. And then again, we're going to adopt this potential outcomes framework. But now we recognize that the past treatment assignments may have an impact on what's going to happen today. So this violates the non-interference assumption. When this non-interference assumption gets violated, we will have to define the potential outcomes more carefully. First of all, the potential outcomes depends on all the past treatment assignments from day 1 to day T. And of course, these are potential outcomes. They stand for the total revenue generated in this single period. And we're going to collect the Y's in the following font. And then now let's look at what are the potential outcomes and what are the assignment vectors. So I'm going to refer to this assignment vector as the assignment path, because it's a path from period 1 to the last period. This is a simple illustration of 4 periods. Every period, we can either do treatment or control. So there are a total of 2 to the 4, which is equal to 16 assignment paths. And following each assignment path, we can observe, for example, in this green line, we can observe Y1 of 1. We can observe Y2 in day 2 of 2 treatments. We can observe Y3 of 110 in day 3. We can observe on day 4 Y4 of, for example, 1100. So basically, following each assignment path, we can observe 4 outcomes. And we are going to make the following 2 assumptions. The first assumption is easy, just to say the potential outcomes are bounded. The second assumption is to assume some notion of M carryover effects, which is to say that the treatment assignments today, yesterday, up to M periods ago are going to have a joint effect on my potential outcome today. So with this notation, we can just write the following notation of Wt minus M to T using the following notation. And to illustrate this carryover effect notation, I'm going to write this Y3 of 111 and compare it with the Y3 of 011. If the carryover effect only lasts for 1 period, meaning that only the treatment assignment that I received today and that I received yesterday matters, then no matter if we do treatment control in the first period, it does not have an impact on the third period's observed outcome or potential outcome. So that's what this assumption essentially talks about. Yeah.
So for a carryover effect, if we have like infinite horizon, but we may have like a decaying factor of these carryover effect, like I wonder how different the results will be.
It will be very different. It really depends on how you model the unknown potential outcomes. So the approach is different, and the results should also be very different. And some very nice references would be, for example, Ramesh's earlier paper on switchback designs, and also, for example, Yu Chen and Stefan's paper on switchback too, where they assume a Markov model to model the potential outcomes Y. And following this Markov model, they can say potentially the effects decreases over time very quickly, and what's going to happen when they're running the experiment. But it's very different approach, which leads to very different results. Thanks for asking. Cool. Moving on further. So I'm going to adopt the shorthand notation here just to indicate what are the treatment assignments in the most recent M periods. And then in the Uber example, M is usually about 1 to 2 hours. And here we define P to be our knowledge of M. But for this tutorial, P is equal to M. So we can just safely think that P is equal to M and then skip the next few things. At Uber, we're interested in estimating the following causal effect, which is defined in this way. So it is comparing treatment and control average across all the time periods. So for example, when there are 4 time periods and when the carryover effect is of 1 period, then we're comparing 2 consecutive treatments with 2 consecutive controls, and we're taking the average across the 3 time periods. So that's what we say by saying a global average treatment effect. So we're going to focus on a Bernoulli design of switchback experiments, where a Bernoulli design is parameterized by the following set of vectors, T1, T2 to Tk. So you don't have to look at the math, but just follow the following example. Let's say there are two small t's, which happens to be 1 and 3. So we have 2 checkpoints at period 1 and 3. Then we're flipping a coin in day 1, which determines the treatment assignment of periods 1 and 2. So we could do 2 consecutive treatments if the coin flip is head up. And if it tails up, then we could do 2 consecutive treatments. And we do this 2 consecutive controls. And we do these 2 consecutive controls for the first 2 periods. And then at period 3, this is another checkpoint. So we flip a second fair coin. And then we determine the treatment assignments of the last 2 periods. So we keep on flipping the coins independently until the end of the horizon. That's what this notion is talking about. And we refer to this as a Bernoulli switchback experiment. So if we flip 2 fair coins in day 1 and day 3, then this induces a discrete probability distribution as follows. With probability 1/4, we also do treatment. With probability 1/4, we do 2 treatments followed by 2 control. With probability 1/4, we do 2 controls followed by 2 treatments. And with probability 1/4, we do always control. And then this defines the Bernoulli switchback experiment's joint probability distribution. We're going to combine it with the IPW estimator. So for this IPW estimator, I'm going to show you using the following example. In this literature, when we assume interference, then the IPW estimator is usually referred to as the Hallways-Thompson estimator. So that's just the name thing, but it's the IPW estimator. So at time period 2, what we're going to observe is that this indicator on the numerator is equal to 1, and the second indicator on the numerator is equal to 0. Because at period 2, we just administered 2 consecutive treatments in day 1 and day 2. And this happens with probability 1/2 because we flip a fair coin in day 1. So on the denominator, we have 1/2. And then what we observe on day 2 is going to be y2 of 1, 1. So then we have, write it down, is 2 times y2 of 1, 1. Moving on to day 3. In day 3, neither of the indicators are 1, because in day 3, we have observed one treatment and 1 control. So it does not reflect what's going to happen with 2 consecutive treatments or 2 consecutive controls. And so if so, then we are putting zeros here on the numerator. And if you look at the denominator, this happens with probability 1/4. Why is this 1/4? It's because we flip a fair coin in day 1, which determines the treatment in day 2. And we also flip a fair coin in day 3, which determines the control in day 3. And this happens with probability 1/4. And so we put a 1/4 in the denominator, but because the numerator is 0, so everything is 0. And then we move to the last period. We do the same thing, and we copy it down. So that's an example of the IPW estimator. So overall, we know that the IPW estimator is unbiased. So we only focus on the variance. And we're trying to, again, apply this minimax optimization framework. We choose the loss function to be the square loss. And we choose to minimizing the maximum risk as defined as follows. And because the estimator is unbiased, this minimax risk has an interpretation of the minimax variance because the mean square error is equal to variance when the bias is equal to 0. So we can solve this problem by reducing it to the following subset selection problem and using some structures of matroid convexity, of discrete convexity notion. We can solve this minimization problem, this subset selection problem, to optimal. And the optimal solution should look as follows. Let's suppose there are 12 periods, and let's suppose that the lag of carryover effect lasts for 2 periods. And then we're going to flip four fair coins. We flip a coin in day 1, we flip a coin in day 5, and then 7 and 9. So that these 4 coin flips splits the entire time horizon into 4 chunks. So that in the middle chunks, they're of equal length, and the length is equal exactly to 2. And in the first and the last period, these are boundary conditions, and the length could be different. And in this case, they're equal to 4, which is 2 times as long as the middle length. So that's the structure of the optimal solution to the previous subset selection problem. And that solves the optimal design of switchback experiment. So just to quickly conclude, I think we're perfectly on time. We have talked about the decision theoretic framework. And under this framework, we have looked at 3 different examples of applying this minimax framework. And I do see there is a lot of potential when people apply this statistical decision theoretic framework, when people are designing the experiments, or even when people are designing the estimators too, to apply the same decision theoretic framework. And the core takeaway is that you should decide which framework that is your favorite, and that depends on how you model the uncertainty of the problems. The paper is here. It talks about many more things, and if you're interested, feel free to check it out. I'm happy to take any questions. Oh, okay. Yeah, the paper name is just the title of this talk. Let me go back here. It's the same title. Thanks.